Yeah, welcome to I think it's only going to be the second recorded fluids and MHD seminar of the academic year. So today we've got Adrian Fraser from the University of California in Santa Cruz. So he did his PhD with Paul Terry and Ellen Zweibel in Wisconsin-Madison on plasma physics, and is now working in Santa Cruz. And he's going to be talking today about MHD shear instabilities. Actually, do you want to load your slides up just to check that they work before I switch my own camera and microphone off?
Yeah.
Okay, great. So we're talking about, fingering convection in MHD, problems with parasites and speculative solutions. So I'll switch off my camera now. Thanks.
Let's see. All right, full screen working?
Yep, looks good to me.
All right, great. Yeah, thanks for the opportunity to talk to you all about this. I've been working on this work with Pascal Garot over at UC Santa Cruz for the last year or so. And this is fingering convection in MHD motivated by what happens in stars. So I'll talk a bit about that. When I was asked to provide a title for this talk, I was ambitious, and I thought that we would have, basically we've got problems with parasites, and we're working on some solutions. And I was a bit ambitious, thinking that I would have the solutions by now. So the solutions, unfortunately, are a bit speculative at this point. But if there's time, I can go into more detail about that. The additional collaborators that are listed below there, Imogen Cresswell, Jeff Oishi, Alexis Kaminsky, they're all involved in sort of offshoot projects that have to do with the speculative solutions. Pascal and I are the ones who've been working together on the majority of this talk. Like Adrian mentioned, I don't have the chat open, so if there's any questions, first of all, feel free to interrupt with questions. Clarifying questions are best asked early. But if there's any questions in the chat, if somebody could please interrupt and let me know, that'd be great. All right, let's talk about fingering convection. So what is fingering convection? First of all, it's not overturning convection. So overturning convection is something that can happen if you have a dense fluid over a light fluid. It's sort of an unstable configuration. I've got a couple examples here. The first one is if you have salt water over fresh water. So salt water is denser than fresh water. The density goes like the concentration of salt, which I'll denote C, or at least it's proportional to it, right? It increases with salt concentration. So if we have salt water over fresh water, that means that because salt water is denser, we have dense water over fresh water, and that's an unstable configuration. So if you take a blob of fluid from the top here and displace it downwards, now this blob of salt water is surrounded by fresh water. That means that it's denser than its surroundings. So, if you put a rock into water, if you throw a rock onto the surface of a lake, the rock is denser than the surrounding water, and so it's going to buoyantly sink. And that's exactly what's going to happen here. Because this parcel of fluid is denser than its surroundings, it will buoyantly sink and just continue on and on. The same deal can happen if you have, instead of salinity gradients, if you have temperature gradients. So because density goes inversely with temperature, if you have a warm fluid underneath a cold fluid, then if you imagine taking this parcel of warm fluid here, which is lighter because it's sort of thermally expanded, if you displace it upwards, then it's now lighter than its surroundings because it has this excess heat. And it'll be like, instead of a rock in water, it'll be like, maybe styrofoam in water, something very light that's been placed in water. It'll bob up to the surface through buoyant forces. So these are just two examples where having a dense fluid over a light fluid can be an unstable configuration. It'll cause the fluid elements to shift around to rearrange themselves. And you can see this in simulations. The previous two figures I got from Pascal's lecture notes. This figure comes just from the Wikipedia article for Rayleigh-Taylor instability. You can do the simulation. You can take a dense fluid and place it over a light fluid and just perturb the interface between them and see what happens. And what happens is, if you perturb this fluid element downwards a little bit, it's now surrounded by lighter fluid. And so it's going to buoyantly sink, just like I showed on the previous slides. It's the same process. Now, as I said, it can happen for anything that gives you a density variation can give you this. So it could be temperature variations, cold water over fresh water, cold water over warm water, or it can be temperature variations. I'm sorry, salinity variations. It's 7 a.m. Please forgive me. So I'm going to denote that with C for the chemical concentration. If there's any stellar astrophysicists in the audience, then think of mean molecular weight, mu, sort of the same deal. All right, so that's overturning convection, what I'll be referring to here. Now, in stars, people care a lot about regions that have overturning convection and regions that do not. So if you consider a chemically homogeneous gas, so forget about the salt gradients or the chemical concentration gradients, and let's just talk about temperature gradients. You have some threshold that the temperature gradient needs to exceed in order for this to happen. So it depends on thermodynamics and gravity and stuff like that. It's the adiabatic gradient, is what some people call it. But basically, if your temperature gradient exceeds some threshold, dt naught dz, then you can have this convection taking place. This is sometimes referred to as the Schwarzschild criterion in stars. Grad greater than grad ad, or I guess grad rad greater than grad ad. But all this means is, there's some minimal threshold, and as soon as your temperature gradient exceeds that threshold, you can get overturning convection. Now, stellar astrophysicists care a lot about this. They look at different radial shells of stars. They treat stars like onions that have radial layers, and each layer they look at what's the temperature gradient in that layer. Is it above this threshold or is it below this threshold? If it's above this threshold, then they call it a convective zone. Sometimes they call it a convective envelope or convective core, depending on whether it's in the core or the envelope. But a convection zone just means that the temperature gradient in that region exceeds this threshold and you have overturning convection. Now, this convection is very, very efficient at mixing things. I think that in MESA, which is a sort of stellar evolution code, they just assume that if you have convection, then it immediately homogenizes chemical concentrations throughout the region. I don't use MESA, don't quote me on that. If it's not actually implemented that way, that's the effect, is that it's so efficient that it really effectively homogenizes the chemical concentrations throughout that region. So it's really efficient turbulent mixing. Regions that don't satisfy this criterion, that are not unstable to convection, are called radiation zones or radiative zones. So they're where the temperature gradient is too weak to drive convection. And in standard stellar models, if there's no convection, that means that there's no mixing. It's not just a matter of less mixing versus more mixing. It's either super efficient mixing or zero mixing whatsoever in historical standard stellar models. Now, in reality, there is still some mixing, and it's small. There is still some dynamics that takes place in radiative interiors that drives some mixing. It's just much smaller than the mixing you see in convection zones, but it can matter. You can have observable consequences of that mixing. It's less well understood what the different sources of mixing in these radiation zones are, but we can tell that there's something going on there, and we want to understand it better so that we can predict the evolutions of various kinds of stars. So that's sort of the motivation for this talk. So we want to understand a certain kind of mixing process that happens in those regions. So the previous slide, I was talking about if you have temperature gradients in the absence of chemical concentration gradients or mean molecular weight gradients, what happens if you have both? So imagine this setup here where we have a temperature gradient, and if you just focus on the temperature gradient, you see that it's warmer on top than it is on the bottom. So this is stable according to the Schwarzschild criterion, because you don't have a warm fluid under a cool fluid, you have the other way around. However, you have a higher chemical concentration above. So, if the concentration gradient is very, very weak and the dominant effect is the temperature gradient, then this is going to be stable to convection, right? You can basically ignore the little white dots. You just look at the red on top, blue on bottom, and you ask, what happens if you displace a parcel of fluid? Well, it's not going to be surrounded by denser surroundings. It's gonna just rise back to where it was before. On the other hand, if you ignore the temperature gradient, if you say that the chemical concentration gradient is the dominant effect here, then you have a dense fluid over a light fluid. So clearly it sort of matters which one is bigger in this case, the stabilizing temperature gradient or the destabilizing concentration gradient. They both matter for determining whether overturning convection takes place. That's the Ledoux criterion, effectively. So here's a nice diagram that sort of maps out different regions of parameter space that I'm very quickly going over here. I want to focus on the top row initially. So the top row is what happens if you don't have any chemical concentration gradients, if you just care about temperature gradients. Along the horizontal axis, the temperature gradient is increasing. So on the left side, we have this configuration here where it's warm on top, cool on the bottom. On the left side, we have warm on top, cool on the bottom, and that's stable to overturning convection. That's a stable configuration because you have lighter fluid on top of denser fluid rather than having denser fluid on top of lighter fluid. As you increase the temperature gradient, like increasing the temperature below on the bottom, once you cross this critical threshold where grad T exceeds grad add, then you have enough heat on the bottom of your fluid parcel that it's now the other way around, that it exceeds the threshold necessary for convection, the Schwarzschild criterion in this case, and you get overturning convection. So once your temperature gradient exceeds a critical threshold, you get overturning convection. On the bottom here, it's depicting what happens in that previous slide where you add the concentration gradient, where the concentration is higher on the top than it is on the bottom. So you can see that the threshold for overturning convection moves to the left. So you no longer need grad T to exceed grad add, rather you need grad T to exceed some smaller number because you have the increase in density from the higher chemical concentration on top. This line here, this is still basically saying you need a higher density on top than on bottom in order for overturning convection to take place. It's still essentially a density argument, or maybe I should be saying entropy. So overturning convection now moves to the left a little bit. The other thing that happens in this configuration is you get fingering convection in this overturning stable region. So this region where we have fingering convection, it is not, it's not overturning convection. It's separate from the region where you have overturning convection. So this region where we have fingering convection is taking place in what we would call a radiation zone, not a convection zone. So this is one of those potential mixing processes that can be taking place in radiation zones. I'm going to walk you through this instability now. So what is fingering convection? Let's consider a stably stratified fluid. And again, by stable stratification, I just mean it's a radiation zone, not a convection zone. So we have denser fluid on the bottom and a lighter fluid on the top. Which means that if we take this fluid parcel here and we displace it downwards, because it has this excess heat, that's the reason why it's so much lighter than the fluid on the bottom. We displace it downwards, it has excess heat. That means that it's underdense. So like a chunk of styrofoam in water, it's going to want to buoyantly rise because it's lighter than its surroundings. Now, it's important for this instability to note that in general, temperature diffuses more rapidly than chemical concentration. So this fluid parcel here is warmer than its surroundings and it has a higher chemical concentration than its surroundings. But the thermal gradient, the temperature difference will diffuse much faster and it'll come into thermal equilibrium with its surroundings while still retaining a little bit of excess chemical concentration. And this again, just because the temperature diffusion happens the thermal diffusion happens much more rapidly than chemical diffusion. Now, it comes into equilibrium with the surroundings, thermal equilibrium with the surroundings. It still has this excess chemical concentration, and therefore it's now denser than its surroundings, right? So it no longer has the buoyant effect of having that excess heat. It just has the excess chemical concentration, and now it's heavier than the surroundings and it will buoyantly sink. So this is the fingering instability. This is what drives fingering convection, also known as thermohealing mixing. It's driven by this chemical concentration gradient. So this is the source of free energy, is all these salt particles or higher mean molecular weight. It has this gravitational potential energy and it wants to sink downwards. That's the source of free energy, and it has to overcome the temperature gradient. So if the temperature gradient is too strong, then the chemical concentration gradient isn't going to be enough to allow this instability to take place. And it's enabled by this disparate diffusion coefficient ratio. So the thermal diffusion has to really be much faster than chemical diffusion in order for this to take place. If they were the same, you couldn't get this instability. All right, so that's the fingering instability. Why are we talking about it in the context of MHD and stars? Well, most of what's on this slide I actually learned in the last few weeks here at KITP. it turns out that there's a lot of people who care about stars who also care about fingering convection. They call it thermohealing mixing, frustratingly, even though there's no salt in stars. Haline means salt. So this was originally studied quite a bit in the oceans, where thermohealing mixing as a word makes sense. And then the word got picked up in the astrophysics community, even though there's no salt in stars, go figure. But why do people care about it? There's a few different stars where people care about it a lot, a few different kinds of stars. One is polluted white dwarfs. So we see metals on the surfaces of white dwarfs, and those metals ought to be sinking below the surface so that we can't see them. And that should happen on a fairly rapid timescale. And so the fact that we see those metals means that they're being actively accreted. So the accretion of these metals onto the surfaces of these stars must balance the rate at which they sink below the surface in order for us to see those metals, right? Otherwise they would just vanish. It turns out that if you take thermohealing mixing into account, that increases the efficiency with which those metals sink. And that means that the accretion rate has to go through the roof in order to explain the fact that you see these metals. So that's sort of the motivation why people care about it in white dwarfs. And this is still an ongoing conundrum. It's a conundrum because a lot of people don't think that it should be that the accretion rates shouldn't be that effective, shouldn't be that high. Massive accretor stars, if you have two very massive stars, one of them is a bit more evolved than the other one. If it loses its envelope to the other star, so it becomes a stripped star and an accretor star, then that accretor star just gained a bunch of more, higher helium concentration material, and it can drive thermohealing mixing. And this very recent paper shows that it actually can be one of the more efficient processes in the star for chemical mixing. And they used a very conservative estimate for thermohealing mixing efficiency too. So it's probably really, really efficient in these stars. The process I know a bit more about is red giant branch stars at the luminosity bump or after the luminosity bump. I'll show you more on the next slide. Basically, red giant branch stars have envelopes that are convective, and they're sort of receding away as the interior is sort of expanding outwards. And during that process, it's driving thermohealing mixing between those two regions. So a little bit of background on that process and when it was studied. It was first identified, I should go back, this Charbonnel and Zahn paper, I think, is the first one that asked the question, should we care about this in red giant branch stars? Then Matteo Cantiello and others added thermohealing mixing to MESA, stellar evolution code, to see, do we see it in stellar models? Should it be happening? What I'm showing here is what's known as a kibbenhon diagram. You can think of the vertical axis as just radius of the star, and the horizontal axis is time. And it is showing different regions, different radial regions of the star as they evolve in time. How do they change? The blue region is a convective envelope. So the white region is not convective, so it's a radiative interior. And you can see that the boundary between the convective zone and the radiative zone goes down in radius over time and then goes back out. So this means that here's your star, here's your convective envelope, and it sort of dips downwards and then goes back out. This sort of peach color here is the hydrogen burning shell, and it also is expanding outwards. And there's this buffer region between the two. Normally, standard stellar models predict that there's no mixing taking place here. But if you take into account thermohealing mixing, it turns out that there can be mixing of chemicals between the convective envelope and the hydrogen burning shell. And that explains certain observations of lithium depletion, C12 to C13 and C over N. Basically, we see that there's signatures of chemical mixing taking place between the envelope and the hydrogen burning shell. And until you take thermohealing mixing into account, you can't really explain why that mixing is happening. So it's nicely solves this problem, or at least people hoped. In these papers, these authors noted that it can explain observations, but it depends on the mixing prescription that they implement. So MESA doesn't actually simulate turbulence. It has a mixing prescription for different turbulent processes that relies on theory to provide constraints for how efficient mixing is. And at the time, there were not very definite constraints on how efficient thermohealing mixing was. There was sort of a wide range of plausible efficiencies. And they found that getting their models to agree with observations was possible as long as you take the more generous estimate for how efficient thermohealing mixing is. Unfortunately, at the same time, hydro simulations were being done by Pascal's group and also other groups. I think this is Pavel Denisenkov. And they found a consistent story, which is that if you run 3D numerical simulations, I think some of these were 2D, but in any case, if you run simulations of thermohealing mixing at low Prandtl numbers, so in regimes that are meant to model stars, the mixing is just far too inefficient to, support the prescriptions that were used in these MESA models, which means that really they should have been using, these authors here should have been using more conservative estimates for how efficient thermohealing mixing is, and that it wouldn't agree with observations because they needed to use generous estimates, not conservative ones, in order to agree with observations. So darn, back to the drawing board. There was a period of time where I think that the astrophysics community thought that surely thermohealing mixing is not what's going on here because of these papers. And then Peter Harrington and Pascal Garot in 2019 had a nice paper showing that if you add magnetic fields, then mixing efficiency goes through the roof depending on the field strength. And even for very, very moderate magnetic field strengths that are plausibly exist in all RGB stars, mixing is efficient enough that thermohealing mixing is back in the game and should be considered. So that sort of sets the stage motivation-wise for the rest of this talk. People need, stellar astrophysicists really want to know how efficient thermohealing mixing is in these regions so that they can know, is it what's responsible for these observations or is it not? Should we be thinking about other processes? And that's what motivates this work. How do we go about doing this? Well, we do a bunch of direct numerical simulations, and we try to come up with models that agree with them so that we can plug them into stellar evolution codes. The simulations that we run are all local Boussinesq models. So thermohealing mixing is a really, really small scale process because it relies on diffusion, and diffusion is really weak in stars. That means that we're looking at very small regions of stars. We're not doing global simulations of like a whole sphere or even a shell. We're looking at really tiny regions where the domain size is much smaller than pressure scale height, and that gives us a lot of room to make nice assumptions that make our simulations faster. So in particular, we're taking a linearized equation of state, and a Boussinesq approximation. So our density perturbation is linear in our temperature perturbation and our chemical composition. We don't have any magnetic buoyancy in this model affecting our density. Then because we can take such a small box, local model, if you imagine that your temperature profile is some non-trivial function in your star, if you plot temperature as a function of radius, it's going to be dependent on a lot of things. If you zoom in into a small enough region, though, you can basically do a Taylor series expansion. You can just take the linear part. You can just do a tangent line, and you can say that in this tiny, tiny region of my star, my temperature is just linear. So in particular, we take a constant gradient throughout our domain. So dt naught dz here is just a constant in our simulation box, so that our background temperature profile just varies as a line throughout our box, and the same for the chemical composition. Then we can look at perturbations on top of those lines. That's the T tilde and C tilde are perturbations to the linear background. And these can actually be treated with periodic boundary conditions in this model. So for those of you who are familiar with shearing box models of the GSF instability or the magnetorotational instability, it's the same kind of deal where you have non-periodic background, but you can look at periodic fluctuations on top of it. And that's just nice because it lets us use pseudo-spectral methods. So we can do a bunch of Fourier transforms and the code runs faster than it would if we had a global model. I'm going to show you the equations that we're simulating on the next slide, but they're going to be non-dimensionalized. And I just want to note that in this game, the standard non-dimensionalization, your length scales are non-dimensionalized in terms of this quantity D, where D is obnoxious. But it's basically just what you get from dimensional analysis. If you map out this process of the blob sinks and then thermal diffusion and all that stuff I was explaining before, and you use dimensional analysis arguments to ask what's the length scale of these fluid parcels, this is the answer that you get. So if you non-dimensionalize in terms of that, that just means that a length of 1 is what you would expect the length scale of this process to be. Everything else is non-dimensionalized in terms of, say, thermal diffusion and other things that just make the equations look simpler. We make a whole bunch of things 1. Here's the equations that we're solving. So again, it's the Boussinesq approximation. So we've got an incompressible flow here, right? We only treat buoyancy. We don't have compressibility. This here is your standard momentum equation. You can see you've got du dt, you've got your advective nonlinearity, you've got a pressure gradient. This term here is the buoyancy term. This is rho g, but because rho is just linear in terms of t and c, and we use non-dimensionalizations where g equals 1, the buoyancy term just becomes t minus c, and then you've got viscosity. The T and C equations here are just standard simple advection diffusion equations. So they're the same kind of thing that you get for the scalar field in Rayleigh-Bernard convection, for example. This W here and this W over R naught here, those are just the advection terms for the background gradient. So that's just U dot grad T naught gets you this W here. So advection diffusion equations. In this whole model, there's 3 physical parameters that emerge that you can vary and see what it does to your mixing. It's the Prandtl number, so viscosity divided by thermal diffusion. Tau here is the ratio of the compositional diffusion to the thermal diffusion. Remember that I said that for fingering instability to take place, that this has to be very different from 1. In particular, it should be less than 1 for the setups that we care about. And then R naught here is the density ratio. If you recall, I said that this instability is driven by the composition gradient, that free energy that wants to settle down, has to overcome the temperature gradient. R naught is measuring the ratio of those 2 effects. So if R naught is really large, then the temperature gradient, which is a stabilizing influence, is very strong, and you can't have this instability, it won't happen. If R naught is very small, then the chemical concentration gradient is a dominant effect, and then you can get fingering convection. If R naught goes below 1, that's the Ledoux criterion for overturning convection. So if R naught is below 1, you have overturning convection. If R naught is above 1, you have either fingering convection, or if R naught is too large, you have nothing, just stability. Here you can see that if you plug these equations into a pseudospectral code and run with them, you get nice, well-developed turbulence that you can do numerical experiments with. Our goal is to predict mixing, right? So stellar astrophysicists want to know how efficient is thermohealing mixing in this star, in that star. In order to do that, they need to know how mixing efficiency depends on these 3 parameters here. So the goal of this work and related work is really to come up with a way to predict mixing efficiency as these parameters are varied. And we're going to talk about mixing efficiency in terms of the Nusselt number and the advective flux. If you have one, you have the other. They're related. One of them is a dimensionless number. So the Nusselt number is a dimensionless measure of how effective turbulent mixing is. And the advective flux is just mixing. So FC here is W times C. W is the vertical velocity. So it's just how much your turbulent motions are advecting fluid up and down. I should say that in stars, like in RGB stars, at least, the Prandtl number and tau, they're both about 10 to the minus 6. The smaller these numbers are, the harder it is to run simulations. So our simulations that I'm going to show you today go down to 10 to the minus 1. I think I've done a couple simulations in MHD at 10 to the minus 2, but that's pushing it as far as what's feasible numerically. So what we really need to do is, get some simulations at 10 to the minus 1-ish, get models that agree with those simulations that are able to predict the Nusselt number at Prandtl number 10 to the minus 1, and then extrapolate those models, those mixing prescriptions to Prandtl number of 10 to the minus 6, and cross your fingers that it works. So that's the spirit of this work. So following that Harrington and Garot paper, we add magnetic fields. We care about MHD, fingering convection. So when we add magnetic fields, we get a Lorentz force in our momentum equation. I'll mention what this coefficient is in a moment. And we have our induction equation for evolving the magnetic fields. And we have resistive diffusion model. We're not taking ideal MHD. The case that we're going to talk about today is one where you have your little triply periodic box that I showed you on the previous slide, and we thread through it as our initial condition a vertical uniform magnetic field. So our initial magnetic field is going to be entirely vertical, no horizontal components, and it's going to be spatially uniform. So everywhere it's going to be just Bz equals 1. Now in this non-dimensionalization, we're going to non-dimensionalize in terms of this B naught. And basically that just means that this coefficient out front in front of your Lorentz force controls the strength of that initial magnetic field. So in a few slides, I'm going to show you some plots where I'm varying HB, and that just means that I'm varying the strength of the imposed magnetic field. So a large HB means a strong imposed magnetic field. All right, so the title of this talk is Problems with Parasites. Parasitic saturation models have problems. I want to talk about them. Before we can get to that, I need to talk about what are parasitic saturation models. So parasitic saturation models are a kind of model that's used to predict mixing efficiency in a variety of systems. In addition to thermohealing mixing, it's been used successfully by Adrian Barker and others in the GSF instability. And there's also some previous work looking at parasitic saturation models in the magnetorotational instability. I'm sure it's been used elsewhere, but these are the examples that I'm most familiar with. But in all cases, you have the same sort of model ingredients that's used to construct a prescription for mixing efficiency, and they can work quite well. That's what I'm showing you here. This is the Nusselt number, so efficiency of turbulent mixing, versus R naught, the density ratio, one of those three parameters that we can vary in our simulations. The solid line here is the predictions from these parasite models, and the points are direct numerical simulations. And you can see that, you know, it's a log scale, so it's maybe plotted generously, but really, as far as we care for astrophysics purposes, this model is bang on. You know, it really predicts mixing efficiency quite effectively in hydro. So, okay, that's what we're after. We want to be able to make a plot just like this, where you have a prediction and simulations that agree nicely with each other, but we want to be able to do it in MHD. So let's talk about what goes into these models. There's two key ingredients that I want to talk about. You can see them both when you look closely at simulations. The first ingredient comes from looking at what the fastest growing modes are. So this is a linear instability. So eventually you get well-developed turbulence, but before you get to the turbulence, you have these unstable modes that are growing exponentially. The modes that grow the fastest are called elevator modes. They're elongated in the z direction. So they have kz equals 0. They're shown here. I'm plotting the vertical velocity, W. And red is an upward moving flow, blue is a downward moving flow, and this is sort of like an elevator up that carries fluid upwards in red, and in blue we have an elevator down that's carrying fluid downwards, hence elevator modes. In what follows, I'm going to use WF to denote the strength of this flow, of this vertical velocity. And it's an instability, right? This is an exponentially growing mode. So note that W is going like e to the lambda t. So I'll use lambda f to denote the growth rate of the fingering instability here. So in order to make a model, you have to make some assumptions to simplify things. And the first simplifying assumption we're going to make is we're going to assume that these elevator modes alone determine mixing. What that means is, you know, advective flux, again, is a volume average of W times C. This volume average, that means that it's an integral over the domain. You can think of that as a summation over all of your turbulent eddies, your small eddies, your medium eddies, your large eddies, your long eddies, your short eddies. All of them go into this total flux. And we're going to assume that of all those eddies, the only ones that matter are these elevator modes, the ones that are elongated in the z direction. So instead of a summation over all of your wave numbers, you just have these elevator modes. So it's just WF times CF. That's these structures. Because these are linear eigenmodes, you can actually solve for C in terms of W. And then you can plug that in, and replacing C with W, you get some coefficient times W squared. The details of this coefficient don't matter. It's something that you can calculate pretty straightforwardly. The end result is that you have a formula for mixing efficiency, F, as a function of some number times W squared, where W here is the amplitude of the elevator mode. So as long as you know what the amplitude of your elevator modes are, you can plug it into this formula and you get your mixing efficiency. Now, this part we've tested. I've got problems with parasites, and the problems are not here. You can do a bunch of simulations and you can plot F versus W squared. And indeed, the slope of that curve ends up being pretty close to this number. It's a nice result. So the problems with parasites that I've got don't lie here. Now, Instead, they lie with the second ingredient. What is the second ingredient? Well, it comes from asking, okay, in the first ingredient, you've told me that mixing goes like the amplitude squared. How do I know what the amplitude is? So you get the amplitude from the second ingredient. And that comes from looking at the very next time step in these simulations. This upward moving flow here is a shear flow because the flow velocity in the Z direction varies in the horizontal direction. So it can drive the Kelvin-Helmholtz instability. In what follows, I'll use sigma to denote the growth rate of the KH instability. So if you know much about shear flows, you know that the growth rate of the KH instability increases with the amplitude of the flow. So a really strong shear flow, think about like wind going over the surface of a cloud. So you got a shear layer like this, and it can cause these characteristic billows. And a strong wind is going to have a higher growth rate of the stability than a weak wind does. And in that picture, we're just rotating at 90 degrees, and now you have what I showed on the previous slide. So it's flow in the vertical direction that varies horizontally. Now, as these fingers are growing exponentially in time, W is increasing in time, which means that the growth rate of the KH instability is growing in time. So it's moving up and up and up along this line. And in order to get the final amplitude, we're going to say that that growth stops when the growth rate of the KH instability crosses the growth rate of the fingering instability, lambda F. You can think of this as sort of an energy argument, say that energy into the elevator modes through the fingering instability has to balance energy out through these parasites that are sucking energy out of the elevator modes. You can think of it as a timescale argument, a momentum balance argument. But basically the end result is we're going to suppose that the saturated WF here, the amplitude of the elevator modes, is determined by the intersection of these two curves, where the growth rate of the one instability crosses the growth rate of the other instability. And when you do that, you can look down here at what the coordinate along the x-axis is, and that gets you the WF that you needed for your first ingredient here. So WF is determined by the intersection of these two curves, which is equivalent to saying sigma equals lambda with some coefficient out front or unity that you can fit to data. And then you plug them into your first ingredient, and that tells you your mixing efficiency. This is a really nice way to think about this stuff because you can add physics and ask, what does it do to the intersection of these curves? In particular, you can add a magnetic field. Magnetic fields don't affect the growth rate of the fingering instability, at least the ones that we care about here. But they do affect the growth rate of KH. So magnetic fields, because of the magnetic tension, stabilizes the KH instability, so it reduces the growth rate. So in blue, I've got the hydro growth rate, inviscid, I should have mentioned that, and incompressible. In orange, we've got the growth rate of KH instability in MHD. You can see that it's lower than the orange curve, so the growth rate in MHD has gone down. And that means that it intersects this curve at a larger value of W. So that means that the amplitude of the elevator modes W goes up when you add a magnetic field. And because of the first ingredient, now that means that mixing efficiency has gone up. So in this framework, you can see that adding a magnetic field causes mixing efficiency of thermohealing mixing to go up. And that's consistent with what's seen in simulations. That was done by this Harrington-Garreau paper in 2019. They considered a single set of fluid parameters, so Prandtl number and tau of 0.1, density ratio R0 of 1.45, and a unity magnetic Prandtl number. They constructed these models and they compared them to simulations. The black line here is showing these parasite models that I've just walked through. And the points here are showing DNS simulations. And you can see that they lie right on top of each other. And this, I should mention, is Nusselt number plotted against HB, so magnetic field strength. You can see that as magnetic field strength is cranked up, mixing efficiency goes through the roof. This red curve here is meant to represent what's happening, like the physical parameters in RGB stars. And basically, magnetic field strength of even like 100 Gauss puts you on this part of the curve rather than this part of the curve here. So mixing efficiency is very sensitive to magnetic field strength in RGB stars, was sort of the conclusion of this paper, one of the conclusions of this paper. This paper didn't look at different density ratios, and it didn't look at magnetic Prandtl number less than 1. And that's important because in stars, the magnetic Prandtl number is less than 1. So we wanted to know, what does that do to the efficiency here if you look at magnetic Prandtl number less than 1. So I'm going to show you a bunch of plots where we vary those numbers, density ratio and magnetic Prandtl number, and they're all going to look like this one here. I've shown you this plot before. This is the Nusselt numbers, so mixing efficiency versus density ratio R0. R0 equals 1 is the Ledoux criterion. So thermohealing mixing acts at R0 greater than 1 and less than 10. And it goes stable at R0 equals 10. So I'm going to show you curves are going to be models, predictions from the parasite model, and points are going to be direct numerical simulations. So again, in hydro, simulations agree quite nicely with models. Here's what happens at magnetic Prandtl number of 1, where you do that Harrington-Garreau model, the parasite model I just showed you. Again, at R0 of 1.45, that's what their paper was on, you see that the curves are, in agreement with each other. They agree quite nicely. But when you increase the density ratio, problems start to emerge, and you see that there's significant disagreement between the simulations and the parasite model predictions. Magnetic Prandtl number less than 1, things get much worse. You see order of magnitude discrepancies between mixing prescriptions and DNS. Now, if I flip back and forth, you can see that the lines aren't moving. It's the points that are moving. The lines appear to move. That's just because I didn't set the plot bounds. Whoops. But this is maybe a bit of a straw man, because the Harrington-Garreau model did not include dissipation in their calculation of the KH growth rate. What that means is that their model didn't have as a knob that you could crank one way or the other the magnetic Prandtl number. So we changed that. We added to that model resistive diffusion, so that you can ask, what does the model predict at Prandtl number 1 versus magnetic Prandtl number less than 1? And it doesn't help. So flip back and forth here, you can see that when you go to the dissipative model, you still have significant disagreement at magnetic Prandtl number less than 1 between the predictions and the model. All right, well, that's a bummer. So we went back to the drawing board, and we looked at, in particular, I mentioned that there's these constants of order unity that you can fit to data in order to see, in order to develop this model. We revisited those, fit them more carefully to new data. It helps, but we still got problems. So this is still like, almost order of magnitude disagreement at the large R0. So at Prandtl number equals magnetic Prandtl number equals 0.1, parasite model is missing significant physics, is the conclusion that we get from this. There's something's wrong. And it's specifically this sigma equals lambda part. So I mentioned before that you can test the first ingredient of the parasite model, and we have, and it looks fine. It's doing great, but this second ingredient has problems. So that's a bummer. I'm kind of running out of time. This is just showing what those simulations look like. So this is at magnetic Prandtl number of 1, just showing a snapshot of this simulation right here at the very large density ratio. This is the vertical velocity at a small, I'm zooming into a very small region of these simulations. And you can see that you get these shear flows, right? You get, this is an upward moving flow in red, and in blue, you have a downward moving flow. And these wiggles here are KH modes. This is the KH instability that's happening at that length scale anyway. This is how you would expect KH to look like. So, the assumption that elevator modes are dominant is clearly valid, because these are elevator modes. They're a little bit wiggly, but they're elevator modes. And the assumption that they're disrupted by KH parasites also appears valid, because that's what's, causing the fluctuations on top of them. So why does the model not work? This is a conundrum. If you ask what's the Reynolds number of these flows, and what's the Alfvén Mach number of these flows, it turns out that this is a region of KH that unfortunately the literature just hasn't studied, it seems. There's not a lot of work looking at what happens to KH in this really bizarre parameter regime. So that's what Imogen Cresswell is working on. I kind of want to skip through these slides. But basically, Imogen has shown that this is growth rate versus magnetic field strength and Reynolds number on the horizontal axis. And you can look at points that have the same growth rate here, which means that the parasite model, right? The parasite model just cares about growth rate. It just cares about sigma equals lambda. So if you take a green point here and a green point here, they have the same growth rate, but they have very different field strengths and Reynolds numbers. The parasite model says that they should be the same amplitude and the same dynamics as far as thermohealing mixing goes. You do the simulations and they're wildly different. Some of them have these strong magnetic filaments that form, others are really blobby. They have totally different kinetic energies and flow amplitudes. So Imogen has shown that the parasite model is missing a lot. I think I'll stop there. there's two key takeaways for this talk, which is that the parasite model at panel number of 0.1, that's not stars. Stars are 10 to the minus 6, but we can't simulate that. At panel number of 0.1, the parasite model fails as soon as you increase the density ratio above what was explored previously, and when you decrease the magnetic Prandtl number to be less than 1. And this is important because this matters in stars. And ongoing work is needed to figure out what physics is missing in these models. So Imogen Cresswell, along with Pascal and I, is looking at details of KH saturation in these weird flows. I'm also working with Jeff Oishi and Alexis Kaminsky on seeing whether non-modal growth is what's responsible here. I'm happy to talk more about that, but that's sort of a whole separate talk I presented at DPP on a couple weeks ago. So with that, thank you all for your time. I'm happy to take questions.